Hello, welcome to my pipeline integrity video that's titled A Closer Look at Corrosion Assessments in the Oil and Gas Industry. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta in Canada. Today I'm going to be talking to you about a corrosion assessment using the NG18 based equations. Some of you will probably know these equations better as the ASME B31G equations or possibly the DNVGL F101 equations. The reason I'm calling them the NG18 based equations is because they were developed by the NG18 committee at the Battelle Institute in Columbus, Ohio, back in the late 1960s and the early 70s. This work was a seminal study in the pipeline integrity industry, and a lot of the work that was done back then, back 50 years ago, has evolved into the various models that we know today, including ASME B31G and DNV F101, as well as others. Now, those of you that have worked with these equations before will know that they're generally considered to be conservative. And in a way, that's a good thing because it means that the pipelines are safe. But if you're the one that's paying the bills on doing all the repairs, you might not be quite so pleased with that level of conservatism. For the last couple of years, I've been studying these equations, and I think I figured out why they're so conservative. So the goal of today is to share some thoughts with you on why they're conservative and what we can do about that, what it means, and perhaps how we can make some improvements to fixing the problems and coming up with more refined and accurate failure pressure predictions for our pipelines. Now, I should warn you up front that some of what I'm going to say here is a little controversial. So I'm going to ask you politely if you can try and keep an open mind, listen to what I have to say and think about things. And then later on, if you have any questions or you would like to debate any of my assumptions, I'm certainly open to having that conversation. So here's our basic NG18 equation, which many of you should be quite familiar with, ASME B31G. We have a remaining strength, which is defined as the predicted failure strength divided by the flow strength. And then we have a big fraction there, a big ratio. On top, we have 1 minus dt, where d over t is the flaw depth ratio with respect to wall thickness. And then on the bottom of that big fraction, we have 1 minus 1 over m d over t. So I'm hoping that a lot of you are quite familiar with that. You will notice that the equation has been stripped down. It doesn't have any shape factors in it or correction factors that you might be familiar with the ASME B31G equations. If you look at original B31G, you'll find that there's a 2/3 factor in there. If you look at the modified B31G, you'll find that there's a 0.85 factor in there. I've stripped this down just to keep things fairly simple. Now, the m that you see there is called the Folias factor. And the Folias factor is a function of a z parameter, and that z parameter is proportional to the length of the flaw squared divided by the diameter and the wall thickness. Now, if you look at ASME B31G or the other standards that use this form of equation, you'll see that there are different theoretical ways that you can do the Folias factor. But ultimately, that Folias factor is it's a length-based factor. Now let's think about how we would typically do a model validation. Whenever you develop a model, you want to make sure that it's working properly, and that can be done through some fairly simple statistical means. So typically what you would do is you would go find some industry failure data. Now for me, I've done this as a paper study, so it really just means going to the library and seeing what I can find there, or talking to some industry colleagues. There's some of you out there that might work at laboratories in the industry, and you might be able to actually develop your own failure data by doing some hydro tests in the lab. Either way works. Now what you would do is you would take that data and you would take the candidate model, in this case the NG18 equation, and you would use that model to predict the failure strength of your corrosion flaw. Simple mathematical exercise. And then what you would do is you would compare the measured, the true failure strength, and you'd compare that to the predicted failure strength. And if your model is inherently correct, those numbers should match up pretty well. So let's do that. First of all, I've found some industry failure data. So I've got two data sets. One I'll call the Corrosion data. And this is from a doctoral thesis from the University of Waterloo from 2000. thesis title is Assessment of Corrosion Defects in Pipelines by Dwayne Cronin. Now, if you look through that doctoral thesis, you'll find that he has 40 complete data sets where he's done some corrosion flaw testing in the lab. What's really good about this data set is that he has 23 full corrosion flaw profiles, which means that we can do a little bit of a refinement of our various calculations. If anybody's interested in trying to do an analysis like this, it's pretty easy to find that Cronin data online. If you just do a Google search on Dwayne Cronin and University of Waterloo, it pops up pretty quickly. So it gives you a good opportunity to take a look at some of the industry data and get a sense of how things play out. My second set of data I'll call the Battelle data, and that's from the Pipeline Research Committee of the American Gas Association, the 5th Symposium on Line Pipe Research, which was November of 1974. That's got 45 data sets. Unfortunately, that one's not quite so easy to find. I only have a paper copy. I'm sure there are a few paper copies floating around, but most of them are probably covered in dust and probably being used to prop open a few doors. Now, the Battelle data is the data that would have been used to validate the original NG18 equation. So that makes it very, very valuable. So let's go through that validation exercise. So here I have a plot where I have the predicted failure strength on the y-axis, and I have the true measured failure strength on the x-axis. And all those red circled data points represent my 85 data sets. Now, what you'll see is most of those data points are below the diagonal that runs across this plot. That means that in general, the model is quite conservative. You'll see that there are, I guess, 4 data points above the diagonal line, and these represent non-conservative predictions. So those would represent unsafe predictions for the pipeline. But the great majority of all our data is below the line, meaning that it's overly conservative. Now, being overly conservative is good in that it means that we are ensuring pipeline safety. But if you're the one that's paying the bills on doing all the repairs, this could well give you quite a bit of heartache. You'll see that there are quite a few data points that are quite low down on the plot there, meaning that there are a lot of repairs that are potentially being done that are quite unnecessary. When you look at the trend line that I've put through there, y equals 0.75x, you get a sense of just how much conservatism there is in this model. Now, some of you will like the idea of conservatism because it ensures safety. What concerns me about this, though, is that if we have some conservatism in the model and we don't have a good explanation for it, we really do have to question the mathematics behind the underlying model. And if we have a question about the underlying mathematics of the model, then we have to really question some of our probabilistic calculations that are being done in support of our pipeline integrity program, and we have to really question some of the reliability numbers that we've got coming out of our integrity program. So my goal here is to try and come up with a model which has got a lot better accuracy. Now, this plot shows you that we've got over conservatism, but it really does not give us a sense at all of why we have that conservatism. So that's what I'm going to show you today that I think is really interesting, and it might catch some of you by surprise a little bit. Here's what I call my atypical model validation. It starts the same way. I go and find some industry failure data, but the next step takes a bit of a turn. I use that data and I use my candidate model, in this case the NG18 equation, and I use it to back calculate what would be the effective Folias factor that was necessary in order to make the model work perfectly, right? So I essentially take the NG18 equation and I kind of turn it inside out, and rather than solving for the failure strength, I'm actually solving for the Folias factor. And I could do that because I already know what the failure strength is from the lab test or the service failure. Now, if I compare that back calculated effective Folias factor to the theoretical Folias factor, so by that I mean compare it back to the equation that you'll get in ASME B31G, those numbers should line up pretty well, shouldn't they? And if they do, then I know that the mathematical formula that's underlying the model is pretty good. So let's do that. So here's my basic NG18 equation again, but I've actually turned it inside out. Before I'd solved for the predicted failure strength divided by the flow strength, but in this case, I'm looking at the actual true failure strength built into that equation. And as you can see, I'm calculating the effective Folias factor. It's a little bit tricky to wrap your head around this equation. I basically had to pull out my pencil and go through the exercise, and this is how things play out. Now, what's interesting with this is just from a mathematical perspective, this is really kind of an unusual looking fraction. So it's got me a little bit suspicious just to start with. Let's see how it plots up. Okay, so here we have a plot where we have the Folias factor on the x-axis, and we have that flaw length parameter z on the y-axis. So as you go from left to right on this plot, you're looking at longer and longer corrosion flaws. Now, you'll see that I've plotted a solid red line, which represents the Folias factor, and that's basically the equation that you get out of ASME B31G. In this particular case, I've used the modified B31G Folias factor. If you were to try this with any other Folias factor, you would get a slightly different curve there. Now, you'll see with the red circles, these are the back-calculated effective Folias factors that come out of those 85 data points that we just looked at a couple of minutes ago. Now, if the mathematics behind the NG18 equation were fundamentally correct, we would expect all those red circles to fall along that curved line, but they don't. So I find that to be a big, big surprise. I would not expect the data points to follow the curve perfectly. I would expect there to be some just natural scatter in the data. But quite frankly, this is really not a good correlation. You see that all of those effective Folias factors fall along a fairly horizontal line there between 1 and about 1.5. And you can see that I've got a dashed red line, a trend line through there, through all of those data points that shows effectively a zero slope. Now, this becomes very important to integrity programs, because what this means is as you go from left to right along this plot, you've got longer and longer flaws. And those longer and longer flaws are increasingly farther and farther away from the theoretical Folias factor. Right? So that means that as your flaws get longer and longer and longer, you're actually getting more and more and more conservative in your prediction if you're using that NG18 equation. Now, I think that for those of you out there that are pipeline operators, this should be giving you a little bit of heartache. I'm assuming that there are times where you send an inline inspection tool down the line, you look at all the flaws that that tool reports, and you do a failure pressure calculation for each one of the flaws, and then you would come up with a dig list. What's really a tricky thing to work around here is that if you find a very long flaw, you know from this plot that that long flaw will have an overly conservative failure pressure prediction. Now, if you do the calculation and it shows you that that flaw should be on your dig list, you're going to be tempted to run out and do a repair, and that repair might cost you $100,000 to go and dig up the pipe. But this plot tells you that the prediction for that particular long flaw is potentially very, very overly conservative, in which case maybe you don't need to go and dig it up. So unfortunately for the pipeline operators, I think that this is going to lead to a little bit of head scratching. This particular plot puts some uncertainty into the pipeline integrity programs that some of you work with. Now, typically we would make the natural assumption that longer flaws have lower failure strengths. I mean, it just seems intuitive. It seems typical. But it's easy enough to check that out. So here I have a plot of the remaining strength, and so that's the failure strength from the 85 data points divided by their flow strengths. And I've plotted that against the flaw length. In this case, I've got millimeters. So as you go from left to right on this plot, you're actually going from shorter flaws to longer and longer flaws. Now you'll see that there really is not a strong correlation there. I do have a trend line there with the blue dashed line, and you can see that going from a 0 length flaw to a 1 meter flaw, you lose about 10% of your remaining strength. That's really not very much. So that's demonstrating that you really do not have a strong susceptibility to flaw length when it comes to the failure strength calculations. You'll see that I've got an R squared value there of 0.04. Now that's really not a strong correlation. That really tells us that that trend line is somewhat meaningless when it comes to how much does length affect the remaining strength. There is a little bit there, but really not as much as the Folias factor approach seems to be implying. So let's get back to the Folias factor and think about that a little bit more. The Folias factor was originally derived to calculate the stress concentration associated with the length tip of a through-wall crack and to determine if it might extend axially and rupture. So that Folias factor is a very, very important part of through-wall crack assessments, which would be used for a leak rupture boundary. And with a leak rupture boundary, you're worried about a short crack that's extending and getting longer, that's extending in the axial direction. I guess if we flip this thing on its head, what's more important is that the Folias factor was not derived to calculate the stress concentration associated with the depth tip of a flaw, either corrosion or crack, and it was not developed in order to determine if that flaw might extend radially and cause a failure. So that's a very, very important thing. We have a factor here that's buried into our NG18 equation, which is derived mathematically and theoretically based on length. But we're not worried about our corrosion flaw getting longer, we're worried about our corrosion flaw getting deeper. So that brings up a very important thing. Direction. When it comes to a corrosion flaw failing, we're worried about it getting deeper, but when we look at the mathematics of the NG18 equation, we have a Folias factor in there, which is mathematically and theoretically all about a flaw getting longer. So that makes me scratch my head a little bit. When we think about why the NG18 equation is conservative, it's because the mathematical weighting of the equation is, in my mind, too heavily focused on length and maybe not so much against depth. Now, if we look at the various industry models, you'll find that there are several industry standards out there that use this basic equation. Before I've mentioned ASME B31G and I mentioned DNV F101, which is, these are the standards that I'm guessing a lot of you will be more familiar with. When it comes to ASME B31G, we have both the original version and the modified version. And then if we want to go to a level 2 assessment, we can go to more complicated things like R-string or P-squared. We can go to API 579, which has got a chapter or 2 or 3 chapters on corrosion assessments. They use a very similar technique in there. We can go to British Standard 7910 and have a similar technique. Now, all of these industry models include some mathematical form of the NG18 equation, but they're using them for surface flaws as opposed to through-wall flaws. So I scratch my head a little bit here and I wonder, is that really 100% appropriate? Now, I'm guessing that there are some viewers out there that are going to point out that the original and modified ASME B31G equations are known to be overly conservative, and that's why R-string was developed. And R-string is certainly an improvement over the basic B31G. Now, the thing with R-string is you're going through a full profile, you're looking at multiple length and depth combinations of the full flaw profile, and you're selecting the lower bound of those various combinations and permutations. And that seems to be a good idea, but if you stop and think about it, you are actually, by going through that algorithm, you are actually removing length from your assessment. When you do your R-string calculation, you're typically going to end up with a shorter flaw than you started with. Now, my argument would be that by taking length out of the calculation, you're essentially taking out error that's associated with the basic NG18 methodology. If you look at the validation that's been done on R-string, you'll find that that's about 30% overly conservative. And those are not my numbers. The 30% conservatism is reported by Colin in his original thesis. And that R-string conservatism of 30% is also reported in a recent PRCI report. Now, that recent PRCI report also came up with a refinement of R-string, which is called P-squared. when you look at p squared has a reported conservatism of 13%. So that p squared really is a step in the right direction, I think, but it's still based on that underlying NG18 equation. And so it still captures some of the over-conservatism associated with the basic model. So let's think about this. We have an NG18 equation that's been used for about 50 years. When you work that equation backwards, you find that the theoretical Folias factor does not match up with the back-calculated Folias factor, and that seems like a problem. And then if you plot the remaining strengths as a function of length, you'll see that there really is not a strong correlation between strength and length. So that's a bit of a head-scratcher. And then when you go and take a look at the theory behind the Folias factor, you come to realize that that is theoretically and mathematically based on length rather than depth. So when I started to do this original study a little while back, I really ended up scratching my head a lot trying to understand what we can do to fix this. What I ended up doing is going back to the original NG18 work that was done 50 years ago, and I recognized that there was a strong focus on length, and I decided to turn the tables a little bit and rederive some of that work, specifically their crack model work, and do it from the perspective of depth as being the focus rather than length. And what I ended up doing is developing something I call the gamma exponent model, or nicknamed the GEM. Now, it can be used for both corrosion and cracking. The cracking model is a little bit more complicated. The corrosion model is very, very simplistic. So here I'll show you that. So here's the gamma exponent model, and this is specific for localized metal loss. This is not to be used for cracking, and this is not to be used for uniform wall thinning. Now I have a remaining strength, which is equal to the predicted failure strength over the flow strength, and that's equal to 1 minus dt, just like we saw before. But here we have an exponent on that of gamma, and gamma is equal to the minimum of the length of the corrosion flaw divided by the radius, and up to a maximum of 1/2. Now, a lot of you will look at this and think that it's just a simple empirical model where I took the remaining ligament, basically pulled that out of the air, whacked an exponent on it, and it seemed to work. It's not quite as simple as that. I've actually gone through a rigorous theoretical derivation based on blunt flaw analysis. When I look at my cracks and look at the depth considerations of a crack, and then I consider how things change for blunt flaws, I actually managed to derive this. So it's not just pulled out of the air. There is a derivation behind it, but it's a little bit complicated to explain to you in this video. I do have an ASME journal paper that would explain that for those people that are interested in the mathematics. Now, one thing that's going to give a few people heartache is that if you look at that gamma exponent, it is limited to 1/2. And that means that the remaining strength, as a corrosion flaw gets longer, is actually limited to the square root of the remaining ligament. And I'm pretty sure that that's going to cause a lot of you some real heartache, because that's not intuitive. I will tell you that that half exponent does come out of the mathematical derivation, and I do have a technical rationale for it. We'll bounce back to that in a couple more slides. Now here's the fine print on the model. All models have fine print. First is that the flaw depth can be modified by a pi/4 factor in order to approximate a semi-elliptical profile. That's pretty standard in the fracture mechanics business. It's used for both cracking and corrosion. Ideally, you have a full flaw profile and you can come up with something a little bit more accurate, but it's a fairly reasonable approximation to call your corrosion flaw semi-elliptical. Now, if you do have a full flaw profile, I have also developed a level 2 algorithm. So it's a little bit like R-string, but there are a couple of key differences. And my ELM algorithm can be used for a more refined prediction. I'm not going to tell you all the details of how that works right now, but I will tell you the results of how well that ELM algorithm does when I use it on the full flaw profile. The flow strength I've used for all the validation is yield strength plus 69 megapascals or 10 KSI. That's pretty standard. I did not mess around with any of the other variations. My derivation is essentially a flat plate solution, and so because of that, I'm limiting to thin-walled pipe. I've come up with an arbitrary d over t of greater than 20, and that's somewhat arbitrary, but it seems to be working. As I mentioned, the gamma exponent limit for the metal loss calculation is 1/2. Now, that's going to worry a few of you, so I'd like to show you a quick demonstration that's actually, I think, legitimate for my data set anyway. So before we took a plot of the remaining strength as a function of length, this time we're going to do a remaining strength as a function of the flaw depth ratio. So there you see y-axis has got remaining strength, x-axis has the flaw depth ratio. We have those blue squares that represent all of my 85 data points. Now, hypothetically speaking, if you were using the basic NG18 equation, if you go through all the rigmarole of the math and you consider a long flaw, what does your mathematics converge to? You would expect your remaining strengths to converge to that red diagonal line. However, with my GEM model, I've demonstrated in my journal article that the more reasonable limit to that is 1/2. So that means that the green dashed line, which represents the square root of the remaining ligament, becomes the lower bound limit. Now, what's interesting here is that all of my data points are above that green dashed line. So I think that this is pretty good evidence for this data set anyway, that gamma exponent limit of 1/2 is pretty good. If that GEM limit of 1/2, if the gamma exponent limit of 1/2 was not correct, you would expect to see a lot more of those data points lying much closer to that red dashed line. The fact that there aren't any in that sort of envelope zone means that the square root relationship seems to be pretty good. Now, what's important here is the gap between the red dashed line and the green dashed line represents over-conservatism in the NG18 equation. And that represents a lot of money being spent by the pipeline operators, perhaps unnecessarily. Now here, if I take the basic GEM model and put my 85 data points, I can do a simple validation, just like we saw before. Here I've got the GEM predicted failure strength on the y-axis, and I've got the true measured failure strength on the x-axis. And in this case, I've included a pi/4 factor to simulate a semi-elliptical flaw. You'll see that the data points line up fairly well. There are a few more data points over the line and represent non-conservative predictions, and there are some data points that are underneath the line and represent overly conservative predictions. But these data points are bunched a lot closer to the diagonal, meaning that the model itself is inherently more accurate. When I put the trend line through there, y equals 0.92, I find that my model is going to be about 8% overly conservative. As I mentioned before, my goal here is to come up with an accurate model which will convince me that the mathematics behind my model is correct. And so this seems to be a step in the right direction. Now at this point, I still don't have great precision. And in order to improve the precision, I have to look at my level 2 ELM algorithm that I've developed for those 23 full flaw profiles. When I do that, I can improve things quite a bit. Again, we have the predicted failure strength on the y-axis, the true measured failure strength on the x-axis, and here my data points seem to line up a lot better with the theoretical line. Y equals 0.98 means that I've got about a 2% over conservatism in that model. Now, I only have 23 data points to look at, but quite frankly, I think that this is really a step in the right direction. If you were to compare this to, say, R-string calculations, the R-string calculations would be about 30% overly conservative. And if you compare it to the p-squared model that was recently developed by PRCI, you would find that that's about 13% overly conservative. So things seem to be lining up, I think, fairly well here. I can do some simple statistics. So for the basic GEM model, assuming the semi-elliptical flaw shape, I have an accuracy estimated at 1.09. And so that accuracy, I mean the mean of the failure ratios, where the failure ratio is defined as the true failure strength divided by the predictive failure strength. And if I take a standard deviation of all those failure ratios, I find a precision of about 18%. So that looks pretty good. If I look at the level 2 Elm algorithm I've developed and look at the full flaw profiles, I can improve that accuracy to 1.01 with a precision of 8%. So it seems to me that that's a step in the right direction. Now, I should mention that a lot of you, I'm sure, are skeptical of that square root relationship. But it seems to me from these statistics that it seems to be working at this point. I would certainly love to have some more data to play with to really confirm this and lock it down. But at this point, that square root relationship seems to be working fairly well. If you're interested in this type of work, I do have 3 real publications, 1 through NACE and 2 through ASME. For those of you that are interested in the mathematical derivation of my GEM model, take a look at ASME Journal of Pressure Vessel Technology. I'll tell you that that is really not an easy read because it's full of math and theory and stuff that will confuse all sorts of people, including myself. If anybody's interested in further viewing, I do have some other YouTube videos. One series is called Pipeline Integrity, Things That Make Me Go, and that's basically a summary of what you've seen here today, but also extended into the cracking world. And then I've got a second series called the Gamma Exponent Model Validation, where I take a look at my Gamma Exponent model and I show the statistical validation work with several other flaw types. Corrosion, cracking, stress corrosion cracking, circumferential cracking, and through-wall crack assessment. So please dig around for those if you're interested. For those of you that have made it this far, thank you very much for your attention. I hope I've given you a few things to think about. I know that some of the things I've said here are going to come across as controversial because they don't seem to be intuitive. I've checked my math. I encourage you to dig up these data sets and try it for yourself. I'm certainly open to conversations about other data sets and how the theory fits in with what we're doing in the world of pipeline integrity. Thank you very much for your time, and until next time, have a good day.